Hi everybody, this is the monthly video of the Academia Mexicana de Optimización Aplicada a la Ingeniería Química. My name is Ezequiel Santibañez. I am professor at Tec de Monterrey, and the presentation for today is regarding the bounds of the variables and how to transform a complex model in a more simple way. For example, we have the acetone production processes. In this case, the acetone is produced from the butyl peroxide in order to obtain ethane and acetone. The peroxide is fed to the reactor, and then some of the ethane that was obtained is separated, and the bottom of the flash is to feed to a distillation column in order to obtain the acetone and some of the raw material in order to recycle, maybe to the reactor in order to increase the global conversion of the system. Each of these equipment has key variables. For instance, the temperature and pressure of the reactor in order to change the conversion, the temperature and pressure of the vessel in order to change the vapor fraction from the feed in order to separate more ethane, and the refill ratio and the feed stage for the distillation columns in order to increase the mole fraction of the acetone or the mole fraction to the stream to recycle to the reactor. To find a feasible solution for this process, we need to solve the reactor design equation. We need to solve the Raspberry equation in order to solve the flash. We need to apply the mesh equations in order to solve the distillation column in a rigorous way. We need to use thermodynamics models, solve energy and mass balances, as well as kinetic models. Consider all these models in the processes could be very complicated. Fortunately, we have process simulators like Aspen Plus in order to avoid that our brain is born. Okay. To know the problem, we need to solve the problem several times. For example, in a sensitivity analysis. In this case, we use the sensitivity analysis tool in Aspen in order to change the temperature reactor, the pressure of the reactor, the temperature of the flash, the refill ratio, and the feed stage. We can obtain almost 40,000 feasible solutions, and the process to decide what is the best solution consider several criteria. It's a complicated problem because we need to consider several criteria. For instance, the reactor efficiency, the energy consumption, the product quality, the safety, as the capital and operational costs. Then we need to identify the variables that are related with the criterion. For example, the operational cost could be related with the boiler duty, with the energy consumption of the condenser, energy consumption of the reactor, and the flash. And we need to minimize the operational cost. The capital cost could be related with the pressure and the temperature for the equipment, because for high pressure, maybe we need equipment with a more thickness, or with high temperature, maybe the material could be satisfy some specification in order to avoid deformation because of the temperature, and we need to minimize the capital costs. In the safety, the temperature and pressure for the equipment, the boiler duty, or the temperature profile for the reactor in order to avoid the hotspot. to minimize the risk. The product quality could be related with the mole fraction of the main product to maximize the quality of the product or to maximize the profit. And the process efficiency could be related with the mole fraction of the raw material to the outlet stream in order to recycle and to increase the global conversion of the system. When we solve all the equation of the system through a process simulator, we can obtain a very defined region. The region is known as feasible region, and is a region obtaining when we relate at least two variables. In this case, there are boiler duty for the distillation column and the condensing duty for the steam column. You can observe that the points are not located in all the plot, all the image. Only in a very defined region, the feasible solutions are shown. If we relate other variables, in this case the boiler duty and the reactor temperature, we can observe a different behavior, but we can identify a feasible region. Also for the boiler duty and the mole fraction of acetone in the product stream, and the refill ratio of the distillation column, the reactor pressure, and the distillation and the boiler duty in the distillation column, and the flash temperature versus boiler duty, we can obtain several feasible regions. What is the importance of this feasible region? That we can identify where is the relationship between variables, and we can identify a potential feasible or optimal solution. This is another behavior, and we can observe that the behavior between variables maybe is not predict easy before to solve the model. But the importance of this feasible region that we can propose some equation in order to simplify the model. In this case, we can propose an equation to say that the duty of the boiler is lower than 1000, because maybe are not important points where the boiler duty is greater than 1000, and we can limit this feasible region by several linear equations in order to obtain feasible solutions. This is the equation produced for this feasible region, but if we consider other feasible regions, we can obtain different equations between the process variables and the decision variables. The boiler duty, the limit for the temperature, and one relationship between boiler duty and temperature for a feasible solution. In this case, we can limit the feasible region only in the region that it's important for us. In this case, maybe the region with mole fraction of acetone lower than 85 are not important, and for the region, this region is, for that reason, this region is eliminated, and only this region is obtained by the proposed constraint. This is another example for another feasible region, and When we analyze several physical regions, we can obtain a mathematical model. In this case, the mathematical model is a linear programming model because all constraints are linear. And the complex model considers the mesh equation, kinetic models, thermodynamics models, reactor design equation. It's reduced to only a 15 equation, 14 constraints for the variables, and one objective function. The objective function could consider the duty of the boiler, the duty of the condenser, and the mole fraction of the product stream. Consider the consumption of energy, the cooling energy consumption, and the product quality. This case is normalized in order to a fair comparison between each of the criteria. But we can solve the linear model and we obtain 15 constraints. The reference ratio is around 0.6. The reactor temperature is around 150. 150, yeah. And the mole fraction is almost 98. And the boiler and condenser is in this range of that units. Then we can simplify a complex model, consider several equations, several behaviors, complex behavior in a simplified model only with 15 constraints, 15 linear constraints. And we can solve this problem using Payomo, using Julia, using GAMS, but we can reduce or simplify the model. Then, based on experimental data or based in data from simulation, we can obtain our own models in order to model more process or to find another feasible solution or to analyze different strategies to solve the problem. For me, that's it. Thank you for your attention. If you have additional questions regarding the simulation or regarding how can we produce different equations for complex systems, we can send me an email. And thank you. That's it. See you soon.